Topic video 6, memory, types and how to use them. So memory is a very important component of any embedded application. It's effectively where we store our code, where we store our variables, so it's extremely important that we have some memory of some kind. So memory devices effectively, if you look at it from a black box point of view, memory devices attached to the data address and control bus of the microprocessor. So you effectively connect any memory enabled device to these three buses. When it comes to the control bus defines how the memory device should communicate with the microprocessor. So because it's called the control bus, it has some aspect of control associated with it. So the control bus handles things like the direction of the data bus. Are we reading from the memory device or are we writing to that memory device? So whether the data bus is in fact going out of the microprocessor towards that device or whether the data bus is going from that device back towards the processor. So we have a means of controlling the direction of the data bus or letting the processor tell that memory device which direction the data bus is effectively going to go. We also have a mechanism of defining the speed of communication. So we have an external clock that the microprocessor provides to this memory device to be able to synchronize when things take place. So we have, because a microprocessor is a synchronous device, the components that talk to the microprocessor also have to be synchronous devices and they all have to be synchronized. So therefore the microprocessor will generally provide an external clock to the various components that connect to it, and therefore the microprocessor defines to that device the rate at which things happen. We also have interrupt handling mechanisms also in the control bus as well. So therefore, if the device has the ability to generate an interrupt, therefore there will be a control line coming back from that memory device back to the microprocessor. So therefore the microprocessor has the ability to address or service that interrupt if one should take place. Okay, the address bus. What is the address bus? Well, effectively the address bus provides the address of the memory location that the microprocessor wants access to. Okay, the address bus is unidirectional. It only goes in one direction, and that is away from the microprocessor. So the microprocessor drives its values onto the address bus. It never reads values from the address bus. So it's simply continually writing different values to the address bus, and then whatever devices are connected to the address bus, they are in fact reading the addresses. The width of the address bus effectively defines the total amount of addressable memory within that effectively the microprocessor can address. So the address bus on the microprocessor, the width of that defines the total size of our address space that we can see from within the microprocessor. The address bus of a particular memory device, so the input address pins on that particular memory device, they will define the amount of addressable memory that lives inside that particular device. So as far as our microprocessor is concerned, we have 16 address pins on our HS12 processor. These 16 address pins make it capable to see 65,536 unique memory locations, so therefore we can see a total of 64K of memory space. On the memory device, on the other hand, if the memory device has only 3 address pins, then it must contain 8 addressable memory words. So I've said words and not bytes because depending on the number of data pins that device has those memory locations could be 8 or 16 or 32 bits in length. It depends on how many data pins that device has to define the size of those addressable memory locations. But the address pins will define the total number of addressable locations. So if we have 3 address pins on that device, then effectively we have 8 addressable memory locations. The data bus is, of course, responsible for moving the data between the microprocessor and our memory devices. The data bus is bidirectional, as I said before. We can use it to read or write values to memory devices. So when we're writing data to a particular memory device, the data bus is actually moving away from the microprocessor towards that particular device that we want to write to. When we're reading from a particular device, then of course the data bus is moving from the device that drove the value we want to read back to the microprocessor. So the width of the microprocessor's data bus effectively defines the word length of the microprocessor. So defines what size of words that we actually moving around internally inside the microprocessor. So as far as we're concerned, our MC9S12X DP512 is in fact a 16-bit processor because it actually has a 16-bit internal bus. So therefore, when it's talking to the various subsystems, whether they're the serial subsystems, analog digital subsystems, or whatever, it is using a 16-bit data bus to move that data around. Okay, so just in a nutshell, how is it that memory works? So to give you an example, I've got a little animation here to show you how a memory transaction would take place when we're trying to read a particular value out of a memory device. So inside our microprocessor we have a command that we're going to run, and this command simply wants to load accumulator A with the memory location 2000. So whatever the contents of the memory location 2000 are, we want to load them into the microprocessor. So what happens is we then pump that value onto the address bus, and it moves down the address bus to the device in question. On the other end of the device, we then define which direction, what it is that we actually want to do. So we tell it we want to do a read, so we set our control line to say we want to do a read operation. So now the memory device has all the components it requires. It knows the address of the element that is in question, and also knows what we want to do with that address. We want to be able to read it. So now, therefore, the device knows it has to get those contents of that memory location and pump them back out to the microprocessor. So if we go inside the device we have a memory decoder. And the responsibility of that memory decoder is to simply take the address that we've given it and simply decode that address to pick a particular word line in our array of memory elements. So the value 2000 has gone into our memory decoder. The memory decoder has then selected the particular row in our memory elements. So it simply picked position 8192, which is 2000 in hex, and it's simply in that row we have the value, hexadecimal value of 45. So it simply activated that row, and then we have the value of 45, which is then simply driven out of those memory elements onto the data bus. So it goes out onto the data bus, and then it simply whizzes along the data bus back to the microprocessor. And therefore the microprocessor will then have the value of 45 hexadecimal in accumulator A. So to reiterate what's happening there, I've written it in words. So when we want to read something out of a memory element, the address of the location that we want to get the value from or write the value to, so the address in question, we simply place that address on the address bus. We then set the control line, so the read-write line, so we set the control bus, the read-write line in question, in particular in the control bus, to define whether we're reading or writing to that memory element. So during a write cycle, the data is also made available at this time as well. So during a normal write cycle, we not only put the address on the address bus, we put the data on the data bus, and then we signal the control line to say that we want to do a write. Okay, so when the device receives the read-write signal, it latches the address off the address bus internally. Okay, the address is then used to drive an internal memory decoder, which activates a particular row of memory elements. Okay, and the row of memory elements is then connected to the data bus. Okay, so if we're actually writing the value to the memory component, then the data bus is then connected internally to the memory elements, and that value on the data bus is actually driven into those memory elements. If we're reading from that device, then of course the memory elements is then driven back through a series of output buffers onto the data bus, and then made available by the microprocessor. Okay, so basically once the memory device is actually read, so it's on a write cycle, once the memory device has actually read those values and driven them onto the memory elements, the transaction's over. Same thing when we're doing a read. Once that value is driven onto the data bus and the microprocessor has read it, the transaction is over. So generally this has to happen within a certain period of time. So generally there'll be a certain number of clock cycles. So once the read line's been, during a transaction, when we simply put the address on the address bus, we put the data on the data bus, and we say we want to do a write, the processor will basically make that information available for a set number of clock cycles. If the device doesn't actually read that information within that set number of clock cycles, then it's lost. Same thing when we're doing a read from a particular memory device. We'll set the address, we'll set the control line to say we want to do a read, and then we'll simply wait a certain number of clock cycles, then we'll read, sample whatever's on the data bus. If the device on the other end hasn't actually met that timing requirement, then of course the data has been lost. So when it comes to memory, memory is basically categorized into two main types. We can either have ROM or we can have RAM. When it comes to ROM, read-only memory, this is our non-volatile RAM. So this is our sort of write to it and it stays intact no matter what we do. This type of memory can only be read to. Traditionally it could only be read to, but there are variations in that and I'll get back to them later. Generally, programs and constants are stored in ROM. Okay, so once we write the values into the ROM, they very rarely change, and they should never change when programs are running. So that's one of the reasons why we use ROM. So a ROM device basically consists of a clock line, a read enable line. So therefore, we can sort of trigger when we want to read. So therefore, that read enable line would be connected to the read pin of our microprocessor. So therefore, when we want to read from that particular device, we simply strobe that read line to tell that device to actually start decoding the memory and making the data available. We also have a data and address bus hooking into this device as well. I've shown here the data is a bidirectional bus, but really it's only a bus that goes in one direction away from the device towards the microprocessor. But as I said before, there are situations when we can actually write to ROM, so I've sort of left it here as a double-headed arrow because traditionally it was only a read-only device, but there are situations when we can write to these components. There exist two main reasons why we want to use ROM instead of RAM. Okay, and as I said before, values that we store in ROM always remain stored under all possible power conditions. The ROM chip can be removed from the system and stored elsewhere, and the contents will remain intact. This is a similar fashion to like when you have a backup hard drive, like a USB hard drive, and you simply dump all your stuff on that USB hard drive, you unplug it from the computer, your data remains intact on that hard drive. Okay, so it's sort of non-volatile. Same thing with ROM. We can simply store things into that ROM chip, we can pull it out of the circuit so it's not powered, we can store it away somewhere else, bring it back later on, and all the data will remain intact. It doesn't actually change. The second reason that we like to use ROM chips is for a security reason. So because ROM can only be read from, we can't write to it. Okay, under normal conditions we can't normally write to a ROM chip, so it can't be accidentally erased, it can't be maliciously damaged, it can't be hacked, it can't be altered. It remains intact through the whole life cycle of that device. So that's one of the reasons why we might want to use ROM, is because it's non-volatile and because it's security. So when it comes to a read-only memory, how does the read-only memory component actually work? Well, we have a series of address lines, and as I said before, those address lines will define the total number of addressable locations we have inside the device. So these address lines pump into an address decoder, okay, and it's simply like a standard logical decoder, and simply those that logical or address decoder will effectively turn on one of the 1024 possible lines. So in this case here we have 10 address lines coming into it, and those 10 address lines can then be used to turn on one of the 1024 possible activation lines that we have coming out of that decoder. So those 1024 activation lines will then effectively connect into our memory elements. Okay, so we have our memory elements in which we have rows and columns of memory elements. I'll get back to that in a bit more detail later on. And then we have, coming out of that two-dimensional array of memory elements, we have it connected up to the data bus through a series of output buffers. So because primarily with a ROM device we're doing read, we need to be able to drive those elements, those values out of those memory elements back onto the data bus. So we have a series of output buffers to simply provide the current required to drive those values down that bus back to the microprocessor. And you can see that we actually have a chip select line, which is used to turn on the output buffers, and memory read line as well. So when the chip select and the memory read line are both on, then the output buffers actually become active. So as I said before about the memory elements, we have this two-dimensional structure that consists of these memory elements. So the size of this two-dimensional structure depends on both the size of our address bus into the device and the size of the data bus coming in or out of that device. So we have a number of columns that equals the width of the data bus. So therefore there we have a number of columns to represent the total number of bits that we can drive out at a particular time on the data bus. And then we have the number of rows, which is equal to the width of the address bus raised. So it's 2 raised to the power of the width of the address bus. So if we have an address bus, in this case here, we have an address coming into the chip that is of size 2. So we have an A0 and A1 pin on this device. Therefore, it can go pump into the memory decoder. The memory decoder then can make active one of the 4 possible bytes, so to speak, that are actually inside this device. So we have a data bus coming out of this that is 8 bits in size, so they're byte size elements, so to speak. So our memory decoder can either turn on the 0, the 1, the 2, or the 3 row, depending on the value that comes on those 2 address pins, A0 and A1. So we have this two-dimensional structure of these memory elements, and effectively it doesn't matter what sort of ROM or RAM device it is, they'll basically consist of the same memory decoder, but it's how these memory elements are actually implemented that basically changes how all this different technology works. So what differs between a ROM and the other ROM variants is effectively how the memory elements are actually constructed. But they all consist of the same memory decoder, and they all consist of output buffers, irrelevant of what sort of PROM technology they are, irrelevant of what sort of ROM technology they are. So when it comes to a ROM, this is historically ROM. Okay, ROM sort of isn't used very much anymore, but I mean, it could always be a situation where you have to work on some legacy equipment, and it may actually be ROM based. So originally, ROM referred to memory that can only be written to once. Okay, and historically when someone talks about a ROM, it effectively is a device that can only be written to once. It was constructed from hardwired logic encoded into the silicon itself. So you had a silicon wafer with the memory decoder on it, the output buffers on it, and you had a two-dimensional array of memory elements. And by default, all these memory elements were set to a logical value of 1. Okay, because each of these memory elements were missing the mask programmed connection. Okay, so we're missing this little connection, so therefore if the connection is missing, all the memory elements were actually driving out a 1 if you actually read to them. So what you could do is by providing the metallization layer, so another layer of the silicon chip, you could actually define which of these memory elements should have a 0 in them. So you'd simply provide that metallization connection for all the memory elements that you wanted a 0 to appear in. So therefore they'd manufacture this chip for you, and therefore you'd have a PROM fully programmed with whatever code you needed it to have. One of the downsides to this is the fact that it's highly inflexible and extremely expensive. So you basically make one chip, it's got only one purpose, and it costs you a lot to make those chips because you've got to get a foundry to do it, you've got to design it the metallization layer, get it right, and get the foundry to mass produce them for you, and you've got to ensure you have a decent market to be able to justify the 10,000 or so chips that you'd have to make in order to get that cost down to a reasonable level. So the pros of using the ROMs, obviously it's non-volatile, so if the power is lost, the contents remain intact. And the benefit of using PROM is, of course, when we turn our processor on, we need it to run our code. So therefore we need to put our code in some sort of non-volatile memory so that when we cycle the power on, the processor can start running the program that we've designed it to run. Okay, if we don't have a ROM section, then our program's just not going to run. So we always need some non-volatile memory in our embedded application somewhere to ensure that when we turn the power on, the program that we want it to run starts running. Of course, the cons is it's extremely inflexible. Okay, and if you make a mistake on that metallization layer, then you've got 1,000+ devices that become landfill. So one of the cons of using ROMs was the fact that if you made a mistake, it was a very costly mistake. So ROMs have its advantages and they have their disadvantages. Okay, but the good news about the ROMs is, so it's not all bad news with ROMs. The good news is that not all ROMs are made equal. There are variants that provide some level of flexibility, and these variants include a PROM, EEPROM, E2PROM, and Flash EEPROM. Okay, so we have these different various ROM technologies that sort of allow us some sort of level of flexibility in some way. So PROM, programmable read-only memory. This type of memory has the ability to be programmed only once. Okay, so it's not a huge step from ROM, but the beauty here is that you don't actually have to get a foundry to manufacture them for you. You can manufacture them one at a time, and you simply got to buy the PROM chip, and then you can simply program them up in a programmer. So we can use a PROM programmer to simply program up our PROM devices, and I've shown here a picture of what a standard PROM programmer might look like. So PROM is suitable for ROM applications where a small number of inflexible ROM are required. So because you're burning them yourself, you don't have to have a large quantity to be able to get the cost down. You simply buy a single PROM chip, burn it up, and you can use it in your application. So the cost is already down quite low already. In situations where you might burn a PROM chip and have it in some sort of embedded application for a great length of time, and then down the track you've updated the code, so therefore you need to change the PROM. You actually then need to pull that PROM chip out, throw that PROM chip in the bin, and burn up a new PROM chip and put it in its place. So it is a bit costly because you're actually replacing that chip, so that you got that cost of that chip each time you do an upgrade. And the other disadvantage is you actually need a technician to do it, because you actually need someone with a bit of skill to be able to tear the device apart, find where that PROM chip is, remove that PROM chip, burn up a new PROM chip, and put that new PROM chip in its place. So it requires a bit of expertise and basically requires a technician to do it. So it's quite expensive. So I guess you could think of a PROM in the same way that you might think of a CDR. When you burn a CD, you make a mistake, you've got a brand new coaster for your coffee mug, but then you've got to get another CD and burn it again. So a PROM is very similar to a CD. When it comes to the memory element of a PROM, so we've still got the same memory decoder, same output buffers that driving the data values back onto the data bus, but it's the memory elements that change here. And it looks very similar to the actual ROM memory element, except that instead of having that link made by a metallization layer, we now have that link made by a very thin wire, and what we call a fusible link. So the beauty of that very thin wire is we can pump a hell of a lot of current down that little thin wire and we can blow it. So it's fusible link, so we can actually blow out the fuse, and therefore it will change its logical state from a 0 to a 1. So therefore, in all the locations where we actually want a logical value of a 1 to appear in those bit locations, we simply blow out the fusible link on that particular memory element, and therefore it will then have a 1 whenever we strobe that particular line. So I guess to sort of describe how these memory elements work, when the memory decoder picks a particular row in our two-dimensional array, the row or the word line becomes active. The word line then turns on that transistor. If that fusible link is in place, then the transistor effectively works as a switch, which means the logical 0 goes through the transistor onto the column line. Okay? If that the fusible link is actually blown and we turn on that transistor, then effectively that column line will have a logical 1 on it anyway. So effectively all the column data lines are effectively pulled high, and depending on if you turn on a memory element that has 0 in it, then effectively that memory element will pull that line low to represent a 0. So by default all the data lines are high, and it's just depending on whether you've got a memory element with a 0 in it, then that memory element will pull that data line low. So if you wanted to program up this PROM memory element, then effectively you would put a high amount of current down the row line, and then in all the memory elements where you wanted there to be a logical one, you would simply ground the column line, and therefore it would make an electrical connection between the word line through the transistor, which would then go through the fusible link down to the column line, and you'd be drawing a lot of current through that fusible link, which would cause it to blow. Okay, so one of the disadvantages of this PROM technology is, of course, once you blow that fusible link, there's no putting it back. You can't regrow it, you can't magically make it reappear. So once you've blown it, it's basically a one-time programmable device. If in fact you had a situation where you maybe made a mistake on the PROM device where you had a location where there was a 0 and it should have been a 1, then you can probably get away with just blowing that 1 bit and making it a 1 instead of a 0. So you can get away in simple situations like that, but they're very rare. Very rarely do you just want to change the bit value from a 0 to 1 in one particular memory location. So our next level of flexibility is our EEPROM. This is our erasable programmable read-only memory. Our EEPROM allows slightly more flexibility than PROM. So EEPROM is a ROM device that can be programmed using a PROM programmer, so we can use the same device we used to program the PROM. We can use that to program our EEPROM. However, the beauty of the EEPROM is the fact that we can erase it using ultraviolet light. So the EEPROM actually has, you can very easily see what an EEPROM, when you're using an EEPROM device, because they have a little quartz window in the top of the IC carrier. So you can actually look through the little window and you can actually see the silicon wafer inside the carrier. Okay, and that little quartz window is basically stored on the top of the ROM package that allows us to see the chip, and we can actually use that little quartz window to erase the chip using ultraviolet light. So to show you what this looks like a bit more close up, you can see on this chip there's a little window, and this is pretty much zoom in on the window, and you can see when you look down in through the window you can see the actual silicon that implements the EEPROM memory elements. So you can see up the top, you've got on the top of the chip you've got your output buffers. In the middle of the center of the chip you've got your memory decoder, so which actually decodes and turns on a particular memory element, and then you've got this big greenish, like squarish area, which is your array of memory elements. So therefore, by pumping ultraviolet light through there, we can actually erase that chip and put it back to its default state. And then we can put it back into the PROM programmer and program it up again. So the window on the top of the chip is made of quartz, as I said, and this is because ultraviolet light will not pass through glass, so therefore we make it quartz, and therefore ultraviolet light will pass through that quartz and then affect the actual memory elements and get them to discharge. So the ultraviolet light charges all of the memory elements on the chip, allowing them to be reprogrammed, and an ultraviolet eraser, which I've shown on the bottom there, it usually takes around about 30 minutes to erase an EEPROM chip. If you left that chip out unprotected in the sun, it would take 3 weeks of sunshine to erase it. If you left it unprotected under fluorescent lights, then it would take about a year to be erased. So generally, as a little bit of a precaution, when they made EEPROMs, they would generally put a sticker over the quartz window, which would sort of allow some sort of protection against it getting accidentally erased. So when it comes to an EEPROM memory element, our EEPROM memory element consists of a slightly different transistor. So instead of the transistor that we had in the previous memory elements, we now have what we call an EEPROM transistor. And how this transistor differs from a standard MOS transistor is the fact that we now have a floating gate. So if you look at the MOS transistor on the left, we have the standard configuration, the source, the drain, the control gate. When you look at the EEPROM transistor on the right, we have a source, a drain like normal. We have our control gate like normal, but then we have a floating gate that sits between the control gate and the silicon substrate. So it is that floating gate that is the magic in an EEPROM transistor. When the floating gate is uncharged, the transistor will function as a normal transistor, which means it will just function as a normal switch. If in fact we charge up that transistor, then in fact we'll have a floating gate, which means the transistor just won't work at all. So therefore the transistor is being deactivated. Okay, but then using ultraviolet light, we can actually discharge those floating gates, which will put it back to its default state, which allows us to then reprogram it again using the PROM programmer. So how a memory element actually looks, we simply have our row or our word line pumping through the EEPROM transistor in this case, and connecting the logic 0 onto our column data line. So if the EEPROM transistor is working like normal, therefore we'll have a logical 0 reflected on the column line. If the EEPROM transistor is being deactivated and it doesn't work, when we pump the activation down the row line, then the EEPROM transistor will not turn on, which means we'll have a logical 1 on the column line. Okay, so that's how we can do a memory element using an EEPROM transistor. So one level above EEPROM is E squared or EEPROM, which is our electrically erasable programmable read-only memory. It's the next level of flexibility above the EEPROM. Okay, it's considered the most flexible type of ROM that we have, and the contents of the ROM can be erased and reprogrammed on the fly while it is actually situated inside the final product. So that's been the disadvantage of an EEPROM and a PROM, is that you generally had to remove it from the device and either discard it or erase it and then reprogram a new one, or reprogram that same one you just erased and put it back into the circuit. So it always required a technician to do it. Whereas with E squared PROM, we can actually program it on the fly while it's still inside the circuit, so we don't even have to take it out. We just simply hook it up to a programmer, program it, and we're done. So this could in fact be done by a technician or done by an end user. Depends on how difficult you've made the reprogramming. The EEPROM can also be used as if it were RAM. However, the access time for a write cycle is extremely slow with E squared PROM, because if you want to write to a memory element in an E squared PROM, effectively you've got to raise it first and then write to it. So there's that two-step process of a raise, then write, which can slow down the entire write cycle. So it's generally not a good thing to write to them very often because they're very slow. And the other disadvantage is that there's usually a limited number of times you can actually write to them. Okay, and it's generally in the order of 1,000. So the E squared PROM that we have on our processor has a write cycle time of about 100,000. So you can write to the E squared PROM about 100,000 times. After that, the E squared PROM transistors no longer work. The floating gate will no longer be programmed. So you have a limited number of write cycles you actually erase and rewrite E squared PROMs. So there is a downside to using them. So when it comes to an E squared PROM, a memory element, effectively we have two transistors. We have one standard MOS transistor, which is used to electrically discharge the floating gate. So we have an E squared PROM transistor which consists of a floating gate, like we did with E squared PROM. It's a slightly bigger floating gate, but it consists of a floating gate. And instead of using UV light to discharge that floating gate, we can use a second transistor to discharge it. So normally when you want to erase a particular memory element, you simply turn on the erase for that memory element and then use that second transistor to actually discharge the floating gate for us. And then we can program up the floating gate using the same sort of mechanism we did with the PROM, by simply turning on the row control line, charging up, putting a fair bit of current through it while we're grounding the data line, and simply run a bit of current through it and simply charge up that gate if we want to program it. So once the transistor is charged, it always shows the logical 1 until it's actually been electrically discharged by turning on that second transistor. So when it comes to flash technology, well, flash technology isn't as flexible. You might think we're getting up levels of flexibility, but flash is not as flexible as E squared PROM. With E squared PROM, you can have byte erasable configurability, so you can erase a single byte using an E squared PROM, or you can even erase a single bit using an E squared PROM. So you've actually got, very fine resolution when it comes to reprogramming. When it comes to flash, reprogramming flash actually requires you to do it blocks at a time. So it generally requires you to do about 512 bytes at a particular time. So you can't just erase and reprogram one byte. You've got to erase and reprogram a whole section of bytes at the same time. But people can handle this. Flash has become extremely popular. You can get flash drives, you get flash in any sort of device these days. Your iPods contain considerable amount of flash. Flash has become very popular, it's very cheap, and it's very cost effective, so people usually put up with this block-wide sort of erasability thing just because it's cost effective. So many microcontrollers also contain a hell of a lot of flash memory on chip. Our processor in question, the MC9S12XDP512, includes 512K of flash memory. That's where the 512 in its name comes from, the 512K of flash. It has flash memory itself has a built-in number of write protection mechanisms. One of these write protection mechanisms is generally you require a high voltage in order to erase flash. So by not providing that high voltage on the board when you manufacture it, you pretty much make your flash write protected. So, but if you want to be able to configure your, be able to rewrite your microprocessor, so to speak, while it's in an application, then you might need to provide that high voltage somehow and just ensure that under normal operations it's off, and only when you're rewriting is that high voltage provided to the chip. The other thing that they provide is a programming algorithm. So each flash technology is completely different. Each manufacturer has their different algorithm when it comes to reprogramming the flash. And by reprogramming the flash, it generally requires you to write a certain bit combination to certain memory locations within a certain flash block. So because the flash blocks are split up to about 512 bytes, if you write a particular bit combination to the first byte and another bit combination to somewhere else which is in that block, but it's generally nowhere near that first location, then you can actually cause that block to actually erase, and therefore then you can reprogram it using another programming algorithm. So there's generally a series of steps that you must go through in order to get the page to erase, and then another series of steps in order to get the page to be able to be written to. So therefore you can't accidentally erase a flash page even if you do provide that programming voltage. You need to follow this particular algorithm to get the page to erase and then get the page to actually program up. So when it comes to the flash memory element, effectively we've got the same thing that we had with the EEPROM memory element, except now we've got a slightly larger floating gate, and it's primarily we need to ensure that I guess the one major difference between flash and E2PROM is the fact that when you're dealing with flash, it's more of a block erase and a block write. So on that note, when it comes to using your flash drives, and you might just be writing a few bits at a time to, a few bytes at a time to your flash drive will actually erase 512 bytes at a time when it's updating it. So what will generally happen is you'll be writing into a bit of RAM that's on your flash drive. So generally you have about at least a 512 byte of RAM to represent the block that you're about to write, and simply you write the bytes in there. And if you don't fill up that 512 bytes, it will simply go to whichever page you're going to overwrite and simply grab what's left of that page and load it into that RAM and then write that entire 512 bytes at one time into that flash drive. Okay, but generally when it comes to USB flash drives, you normally have a lot more than 512 bytes of RAM, just so you can cache up a lot of data, and then the slow writing process to flash sort of doesn't slow you down as much. But yeah, be aware that when using flash, it's block erase, block write. So the other type of memory that we actually have is our RAM memory, which is random access memory, which is kind of a screwy name for it, but this is the historical name for it, because memory is not random access anymore. It's not randomly reading from the memory. You can read anywhere. You can read sequential memory locations. So it's no longer random access memory, but it's historically the name we use to define read-write memory. So our RAM is primarily used for the storage of program data. You should not use RAM to store your actual program, because RAM is volatile. It can be accidentally written to. You can have your program modified during the normal running of the program. So in order to do some sort of write protection of your program, you normally put that in ROM. So RAM is primarily used for storing variables. It is extremely volatile. Turning the power on and off will lose the contents of RAM. So if we get fluctuation in the power sort of drops down a bit and our voltage regulator cuts out, then we lose the contents of our RAM. Okay, data can be easily written and read from RAM quickly and efficiently due to the nature in which we store the information inside that RAM. And because of the way we store that information, there is no limit to the number of write cycles we can do to RAM. RAM is designed purely to be hammered and written to continuously, so therefore there is no limit. Okay, we have no floating gate transistors here that can break down over time. These are simply memory elements designed to be written to continuously. So when it comes to random access memory, the basic random access memory, like any other memory device, the RAM chip connects to the data, the address, and the control buses, like normal. Externally, the RAM chip differs from the ROM chip in only one way, and that is that it contains an additional control line to define when we want to write data to that particular device. So it has an additional control line, which is the write line. So it has a read line, because we obviously want to read from it, but it also has an additional line, which is the write line. However, internally there are considerable differences to the RAM, so the RAM differs quite significantly from the ROM when you look at it internally. So internally we have the same things that we had in the ROM, so we'll look at those first. We have our address decoder, because we still need to be able to take the address line and turn on a particular word line in our memory array. We still have our output buffers, because we still want to be able to read from this RAM device. But the difference is that now we actually have a input data control mechanism as well. So therefore, if we want to write data to it, we simply have a series of write buffers that are then inside the input data control mechanism to ensure that we can write data into that memory array. You also notice our memory array differs slightly, as in now we have two ports into that two-dimensional array. We have an input port as well as the original output port. So when it comes to random access memories, effectively we have two types, SRAM and DRAM, and they are the only two types of memory you have. The computer-based memories like the DDR RAMs, they are a variation on DRAM. Okay, so we have two primary technologies of SRAM and DRAM, and all the other memories are based on these two primary technologies. When it comes to SRAM, our static random access memory, our SRAM has extremely low latency. It's very quick. It's the fastest memory technology that is currently available. And generally the caches of modern day CPUs consist of SRAM memory. So your L1 and L2 caches and L3 caches are generally SRAM technology. The basic SRAM memory element is made up of 6 transistors. So previously the memory elements in our ROM technology consisted of no more than 2 transistors, and that was with the E² PROM, but generally 1 or 2 transistors per memory element in our ROM technologies. In our SRAM technology, we've got 6 transistors making up a single memory element. So the SRAM memory element occupies a lot of space on the silicon wafer, because now we've got 6 transistors. Transistors are quite big on a silicon wafer in comparison to other components. So now we've got 6 of them for each memory element, so each bit memory element now consists of 6 transistors. And therefore SRAM is expensive and generally only available in small quantities. So that's why you don't have 3 or 4 gigabytes of cache inside your processors, because that would be extremely expensive, and the silicon chip that would result would be absolutely huge. So an SRAM memory element, as I said, consists of 6 transistors, and these 6 transistors are effectively configured in an RS latch-like configuration. So therefore, using the word line, we can turn on a particular latch, and therefore we can read the particular bit value off the BL line, the bit line. So therefore the bit line would be connected to the output buffers, which would then drive that particular bit out the data bus. But one of the byproducts of this particular memory element is the fact we have the not BL line as well. So therefore, in our microprocessor, when we have our register sets made up of these sort of SRAM-like elements, we can quite easily get the not out of a particular register simply by latching the other output bit line. So instead of latching the bit line, we can latch the not bit line through a multiplexer to the actual data bus. So we can quite easily do a not inside a microprocessor just simply by latching the other output line. So an SRAM element consists of effectively 6 transistors, quite a lot of space on the silicon wafer. DRAM, or the dynamic random access memory, is a type of RAM capable of holding data as long as each memory element is continually written to. Okay, a special logic circuit, referred to as a refresh circuit, basically reads each column of that two-dimensional memory structure and writes the values back. So it simply reads all the values back, writes them all back. So it simply does it a column at a time. So it does it relatively quickly. The refresh circuit performs the task over 100 times a second. Okay, and if the memory elements are not refreshed at irregular intervals, then the data contained inside the DRAM memory element will be lost. Okay, so you need that refreshing circuit to continually refresh those memory elements, otherwise you'll lose data. Okay, and due to that overhead of that refreshing circuit of each element, DRAM is generally a lot slower than SRAM. So generally between each write, you've got to keep refreshing those memory elements. Therefore, your read access time can be quite slow. However, the DRAM has the advantage of occupying 1/4 of the space on the IC than an SRAM, so therefore you can get higher densities, you can get smaller chips, and therefore smaller, high densities means a cheaper cost. So therefore the overhead of the refresh circuit is tolerated in order to allow the use of large capacity and yet less expensive memory. So the dynamic random access memory, each of those DRAM memory elements consists of only one transistor. That's why it's small. It's only got one transistor, but it also has one capacitor. Okay? When that capacitor is charged, it holds the bit value of 1. If it is discharged, then it will hold a bit value of 0. The purpose of the transistor in that memory element is simply to read the value of the capacitor. So the problem with the capacitors is that they hold their charge for only a limited amount of time, and when we're talking about capacitors inside a memory element, these are going to be extremely small capacitors, so you can see that these capacitors are going to fade extremely quickly. They're going to be pretty much gone if we don't refresh them. So that's why we've got to constantly keep refreshing the memory elements, is to keep sampling each memory element and then recharging those capacitors so we can maintain that bit value. So if your memory contains the bit values of 0, then you really don't have to refresh it. But if it's a value of 1 anywhere in those bit values, you've got to refresh them, because if you don't refresh them, then they're all eventually going to end up representing 0 in value, and you don't really want that. So we simply have a memory element which consists of a single transistor that allows us to read the value in the capacitor. So we can charge up the capacitor, and then we use the transistor to read it, and then we've got to keep ensuring that we keep refreshing those capacitors to make sure they don't lose their charge. So the pros and the cons of DRAM versus SRAM. The use of SRAM has 2 major advantages over DRAM. SRAM does not require that external refresh circuit, which makes it easy to implement the DRAM. So circuits which use SRAM are relatively a lot more simpler than the circuits that use DRAM. Access times for SRAM are much lower than DRAM. SRAM can give you access times as low as 10 nanoseconds as opposed to the average of 60 nanoseconds for DRAM. And of course, the cycle time of DRAM is much shorter, as memory does not need to be refreshed between each read. So therefore, SRAM is a lot quicker and a lot simpler to use. However, the use of SRAM has 2 disadvantages, and this is SRAM is much more expensive than DRAM, and of course SRAM occupies more area on a silicon wafer than DRAM, which of course impacts on that expense, makes it more expensive the more space it takes up on a silicon wafer, and plus it also means that you can't have chips with lots of SRAM, because putting lots of SRAM on a silicon chip will make the chip very, very big, which means you can't use it in mobile applications, or you can't use it in a lot of applications. You try and keep that size of that chip down and try and reduce that power consumption as well. So when it comes to interfacing to memory, so interfacing a microprocessor to memory can either be difficult or easy, depending on whether you've done your homework first or not. So before jumping into designing a embedded circuit, you need to think about what are the requirements of your microprocessor, what are its timing requirements, and what components can I use that actually meet those timing requirements of that microprocessor. So in a microprocessor-based system, the microprocessor is the master. It dictates everything as far as when things take place. Okay? It defines when the memory device is accessed, defines when data is made available to it, or when data is read from the data bus. So as I said before, generally during a read transaction, you simply put the address on the address bus, you set the read line in the control bus, and then you wait a set number of clock cycles, and then the microprocessor will sample the data bus. So if that memory device you've chosen can't provide the data within that short window of opportunity, then it's an absolutely useless component and you shouldn't use it. So it pays to do your homework first. If you can find devices that will talk to your microprocessor in the appropriate time, then you'll make your life a hell of a lot easier. So the microprocessor will define the timing for the other components. So you need to pick components that meet the requirements of the microprocessor. So when it comes to connecting a memory device to your microprocessor, you basically need to do the following. You need to connect the external clock from the microprocessor to the memory device's clock pin, so therefore you can ensure that all the components are talking at the same rate. You connect the read-write pin of the microprocessor to the memory device's read-write or the read-enable pin, depending whether it's a ROM or a RAM device. So you connect them up. So therefore you've connected the control bus, and these are the two most important control pins that you need to connect. When it comes to connecting the data bus to the device, you basically connect the data bus of the microprocessor to the data bus of the memory device, ensuring that all the bits align properly. If the data bus is different size, then you align the smaller bus to the least significant bits of the larger bus. So generally, if you've done your homework right, you'll be picking components, memory devices in which the buses are the same size. But if you pick a memory device in which the bus is actually smaller than what the microprocessor provides, which is done in a lot of situations. You'll pick a memory device with a smaller data bus than the microprocessor. It doesn't matter. But then what you need to do is you need to align the data buses, and you align them to the same pins, I suppose. You align D0 to D0 on the microprocessor to D0 on the memory device, and so forth. So effectively you align the smaller data bus to the lower significant bits of the microprocessor's data bus to make sure they align properly. So therefore any value you pass from the memory device to the microprocessor maintains the proper magnitude value of that number that you're transmitting. So if you get the data line out of alignment, then you're simply either pumping through a value that's twice or 4 times or 8 times bigger than what it should be. So you always ensure that you align the data buses to be the same pins. When it comes to connecting the address bus, this is a situation where you will have misalignments. You'll have different sizes of address buses, because your microprocessor will have a very big address bus because it needs to see that address bus will define the entire memory map that your microprocessor can see, and you don't want a memory device to occupy that entire memory map. You want to have a series of memory devices in there because you want some ROM, you want some RAM, you want some I/O devices. So you will have a mix and match of different devices throughout your memory map. So therefore your memory devices will have smaller address buses than what your microprocessor does. So then when it comes to aligning the address bus, you simply align them to the least significant bits. So you'll connect them up so that your microprocessor address pins will line up with the memory device. So by ensuring that you get that address bus aligned in that way, so A0 maps to A0, A1 to A1 and so forth, you can ensure that that memory device will occupy continuous memory locations. So in this example here, we will have the register inside the memory device appear at memory location 0, the next one at memory location 1, 2, 3, all the way up to memory location 7. So you'll have them all in nice continuous memory locations. So it's very important that you align them. If in fact you align them incorrectly, so therefore you have the memory device connecting to, say, A1, A2 and A3, then you'll have some weird things happening with the memory map. Okay, and if you write out what the combination of the address patterns, you'll actually see what takes place, and I'll show you an example of that a bit later on, what happens when we do some strange things with the address bus. So if we have a microprocessor with a 6-bit address bus and we connect it to the memory device that only has a 3-bit address input, what does this do to our memory space? Okay, so if we only connect up the lower 3 bits in this situation, what happens to our memory space? Well, since we're only using the bottom 3 bits of the address bus and the top 3 we're just simply ignoring, they're not connected to anything, this means that the 8 memory locations on the device will be mapped to our microprocessor to XXX00 to XXX111. So therefore I'll put X's in all the don't cares. So therefore effectively what will happen is that memory device will appear at multiple locations. So effectively address 00001 inside our microprocessor will be exactly the same location as 111001. Okay, because the top 3 bits we don't care. They can be whatever, 0 or 1, any sort of combination, and they refer to similar memory locations. So it depends on so it's only the lower 3 bits that actually define the particular register inside that particular memory device, or the memory element inside that memory device. So therefore our entire memory space would actually look something like this. We'd actually have that memory device repeating every 8 memory locations. Because our memory device had 3 input address pins, it meant it effectively had 8 addressable memory locations. So therefore it will repeat every 8 memory locations up to the full limit of our memory map. Okay, so that's what happens if we don't do something with those top 3 address pins. We simply have it repeat. And in some situations, if you've only got one memory device you want to connect, you don't care about the rest of the memory space, then yeah, bugger it, let it repeat. And therefore you can simply, by accessing it in the lower 8 locations, you're simply dealing with that device. You don't worry about the repeated bits in the memory map. I mean, you could make it so it only appeared once, but you know, if you've only got one device, why bother going through that trouble? So let's assume for an instance that we want to go through that trouble. We want to make sure that it only appears once in our memory map. So how could we ensure that this device only occupies 8 bytes in our memory space and not the entire memory space? Okay, what role could the 3 most significant bits of the address bus play? Could we use those most 3 significant bits in some way? Well, yes, we could. What we could do is we could actually fuse all 3 of those top address pins by using an AND gate, and then pump the output of that AND gate to a chip enable for that particular memory device. Okay, so now that AND gate is now being used to make our device appear in only one spot in our memory map. So now that the 3 most significant bits of the address bus are all high, the memory device is enabled. So only when we've got the memory location, or sorry, memory address where we've got 111000 to 111111 are we actually talking to that device. Okay, so by using the AND gate and fusing those top 3 bits through that AND gate, and then using that output of that AND gate to simply turn the chip enable pin, we can actually have that device turn on only when the 3 most significant bits of our address bus are high. So the chip enable is effectively like an on-off switch for our memory device. On some chips it could be called a chip select, but it's generally called a chip enable, so it can either be called CE or CS depending on what sort of chip you use. But generally that works like an on-off switch, and by using a simple memory decoder like we have here with an AND gate, we can simply turn on that device when the top 3 bits of our address bus are actually high. So as a result, our memory map will now look like this. So therefore the rest of our memory map is actually empty, and it's only the top 8 bits of our memory map that actually have that particular device now, because it's only in the top 8 locations of our memory map is where A5, A4 and A3 are all set to 1. Okay, so that's how we can sort of make the device appear only once inside our memory map. So we've got another example here. We've got multiple devices that we want to appear in our memory map. So what we've done here is we've actually wired up those chips. So these are all 1K chips. So therefore all those 1K chips have 10 address lines to represent the 1024 bytes that we have inside those chips. We've connected all the data lines up to the data bus. So each device's data bus will connect to the microprocessor's data bus. Each of those 10 address lines will connect up to the lower 10 address lines of our microprocessor, of our address bus, okay? And then what we do is we use the next 3 address lines of our address bus to then select a particular 1K block. So in this example here, we're actually only showing 2 in the picture, but effectively there are 8 different chips, 1K chips. So effectively we've got 8K of chips, and we've got 8 of them, and using those top 3, or using those 3 address lines from A10, A11 and A12, we can actually then pick which one of those 8 chips we actually want to turn on. So we pump it through a decoder, and then the decoder can simply activate one of the 8 on lines, and one of those 8 on lines goes to each one of our chips, to the chip enable or the chip select of that chip, which then turns that chip on. So when you give it a particular address, only one of the chips will turn on. Okay, so in the situation where you simply have A10, A11, A12 set to 0, then the first chip is made active. When you have A10 set to 1, A11 and A12 set to 0, then it'll be the second chip that's made it active, and so forth. So therefore you can turn on a particular chip by simply selecting a particular memory address. Okay, and because we aligned those address lines A0 to A9 to the A0 and A9 of each chip, therefore those chips will appear in continuous memory locations inside our memory map. So to give you another example of a memory map, so to speak, this is the memory map that we use inside our processor. And you can see that inside this memory map we have various memory mapped technologies. We have our I/O register set living in the bottom 2K of memory. So on the bottom 2K of memory we have our GPIO registers, our analog to digital converters, our timers, our pulse width modulators, our serial subsystems, and all our other various control registers for the microprocessor itself. All live in the lower 2K of memory on our memory map, so they are all memory mapped I/O devices. Then we have a 1K EEPROM window that we can use using the ePage register to simply pick a particular EEPROM page within our total ePage memory that we have access to. We then have a 4K RAM window that we can set to any sort of 4K page inside of our 32K RAM space that we have, and then we have a fixed 8K RAM window that is fixed at from 2000 on to 4000. So that's our fixed 8K page window that we can simply put our data variables in. We then have a 16K page flash, unpaged flash, so this is fixed at 4000, so this is where we can simply put our program space, so it's flash, so it's ROM, so we can stick our program there. And then we have our paged window for our flash, therefore we can see anywhere else in our 512K RAM, 512K flash memory that we have. And then we have another 16K fixed flash as well. And in part of that last 16K flash unpaged section that we have a 2K reader-only portion. It's write protected, currently contains a serial monitor, and there's no way in the world that we can currently change it without having a BDM pod that allow us to erase it. So under normal operations, we cannot erase that lower last 2K, the highest 2K of our flash. Okay, and that's primarily the reason why we have our vector table mirrored into the next section that we can write to, which is from F7. So F700 to F7FF is the next writable section of flash that we can use, and that's why we put our our interrupt vector table at that location instead of in the top 2K write protected chunk of memory. So, should you require further assistance, then please do not hesitate to ask your demonstrator, post a question on the forum, email me the convener, make an appointment to see me, knock on my door, track me down, ask me after the lectures, ask me after the shoot, whatever works for you. I don't really mind, but please just make sure you get all your questions answered.